Good time of the day, everyone, and welcome to the series of online technology meetings provided to you by EPIC. And today we discuss the exciting topic of hybrid photonics integrated circuits. Let me remind you that EPIC is the largest photonics industry association in the world. We have over 800 company members all around Europe and outside, and we're here to provide you with technology, marketing, and business consultations. The agenda of the meeting today is extremely well done, and we have exciting speakers to share with us all the aspects and views in this area. We'll start with the presentation provided by Fraunhofer HHI, and Moritz Kleiner will be the speaker, followed by Exceliprint and Ruggero Loi, the supply chain scientist, will tell us about the microtransfer printing techniques. Then presentation by Vanguard Automation with Laura Horan, the staff engineer from Vanguard, and Jörg Smolensky, the business development manager from Nanoscribe. After this, we hear from Chilas BV and Dimitri Geskus, Chief Technology Officer, and VPI Photonics, presented by Andrei Palatinsky, Principal Application Engineer. Last but not least, we'll hear from the CEO of Alcyon Photonics, Jimena Garcia Romeo Nunez. So welcome everyone, and I'm glad to see so many familiar faces in the room. Just to mention that apart from our speakers, we have a lot of participants at the meeting today that represent basically every ring of the supply chain in hybrid integrated circuits. Just take a look at this impressive picture. We have equipment manufacturers, end users, integrators, contact manufacturers, component and modules manufacturers, metrology and testing, materials, consultants, software and design, and of course a lot of R&D and the research organizations involved, which just shows that the topic is so exciting, and I'm looking forward to hear what's the updates from you now. Without further delay, I would like to invite the first speaker to introduce us to the topic and also tell us the updates at Fraunhofer HHI. So Moritz Kleiner will be the first speaker. Moritz, whenever you're ready.
Yep, thank you. But here it tells me that I cannot share while someone else is sharing. So I think you need to stop sharing, and then now it should work. Okay. So can you see it okay?
Yeah.
Okay, perfect.
All yours.
Thank you very much for the kind introduction. Pleasure to be here with you today and talk a bit about our activities in hybrid photonic integration and the versatility of hybrid photonic integration technologies for various applications. So as I'm the first speaker of today, Dimitri has asked me, Ivan has asked me to introduce some aspects of photonic integration, hybrid photonic integration, to get everybody here in the workshop up to speed of what we are talking about. So that's why I just added 2 slides to my talk just today. Well, I'm sure that everyone is aware that in photonic integration, we want to integrate lots of optical functionalities from bulk optics into miniaturized chips. For example, lasers, detectors, waveguides, filters, in order to provide multi-purpose photonic integration platforms that can cater for a broad array of applications. For example, transmitters for communications, readout units for sensors, photon sources for quantum technologies, and the like. There are several integration techniques that are being employed. One One, of course, is monolithic integration, where the actives and the waveguides are on the same die. So everything has to be fabricated in a semiconductor material system, mostly indium phosphide, because it has a band gap that is suitable for near-infrared light emission and detection. And one great advantage is that once you have fabricated your chip, you have your optical subassembly, so you do not need to do any assembly at this stage, just some module packaging, fiber coupling, that's it. However, you're intrinsically limited by the properties of the material. For example, if you want to say go to shorter wavelengths, for example, indivisible, we want to fabricate a laser that emits indivisible, a tunable laser, then this material would be out of question. So if you want to go to other wavelength regions using a monolithic integration approach, you have to do all the development all over. And the second thing that you need to take into account in monolithic integration is that even though you might be able to fabricate, so for example, lasers and detectors and modulators and waveguides on a single chip, there usually are some trade-offs in the manufacturing between all these different components. So usually the specifications that you get from these elements on a monolithic integrated circuit are not as high as you would get from components that are fabricated on dedicated wafer runs. For example, dedicated lasers, dedicated modulators, dedicated detectors. In hybrid photonic integration, on the other hand, waveguides and actives are fabricated on separate dies. So actives, again, usually semiconductors. These can be indium phosphide, for example, for lasers, but can also be gallium arsenide for lasers shorter wavelength, or silicon detectors, coupled to passive waveguides, for example, in silicon nitride, polymers, thin film lithium niobate, and nonlinear optical elements, for example, periodically pulled lithium niobate and KTP. Here on the top are some examples from recent hybrid photonic integrated circuits, one from HHI. Then we have here a hybrid laser from Lyonics, and I am sure that Dimitri will talk a bit more today about hybrid lasers. And here one recent example from EPFL for the laser at shorter wavelength. And for these hybrid integrated circuits, obviously you need to assemble the different dies. You can do this via butt coupling. You can do this, for example, also via microtransfer printing that we will probably hear more about in the upcoming talk. But you have the advantage that you can combine the optical components and novel functionalities on a single chip without having to redevelop everything from scratch once something changes. And also you have advantages in terms of yield management, because this hybrid integration approach allows for the use of known good dies that can be combined onto a single PIC. So these were the two general introductory slides that I wanted to present. And with that, I would like to go into some more details of what we are doing at HHI in terms of hybrid photonic integration. So what we do is we combine single components, semiconductor components such as lasers, detectors, modulators, single photon detectors, and passive waveguiding platforms, as I've shown you before. But what we also do is we integrate there micro-optical bench approaches, micro-optical elements such as isolators, thin film filters, crystals, and lenses. And this I want to introduce briefly to you today. Just a quick overview of what the waveguiding layer looks like. This is based on polymer materials that are commercially available. fabricated on 4-inch, 6-inch wafer scale. We have the scaling to 8-inch on the roadmap. We use single mode waveguides with rather low refractive index contrast, and we can just dice the chips, and no coating and polishing is required because the refractive index of the waveguides is quite close to the refractive index of the standard single mode fibers. And here we have one example of a hybrid integrated functionality on these chips. In this case, a tunable laser, where we have an indium phosphide element here that is HR coated on the backside and anti-reflective coated on the coupling interface that is button coupled towards a polymer-based chip with a waveguide where we have an inscribed Bragg grating. And this Bragg grating acts as the second mirror for the laser cavity, and it is tunable by means of thermo-optical tuning. And in this way, we were able to realize tunable C-band lasers, but the same approach can be used for shorter wavelength. So this is one of the beauties of the hybrid integration concept. So we leave everything as is, adapt the parameters here a bit, exchange the gain chip, and in this way we can realize tunable lasers for 1064 nanometers and for 785 nanometers using other gain elements. And these lasers are then building blocks that can be used to fabricate more complex photonic integrated circuits, for example, for sensing, for communications, and for quantum technologies. One other functionality that I briefly want to introduce is the use of thin film elements. So despite having optical filtering functionalities that is waveguide integrated as is usual in photonic integration, we also have the possibility to use these thin film elements. These are basically very thin dielectric layer stacks, as you know them from classical optics, where you have coated lenses, dichroic mirrors, and the like. And in this way, we are able to transfer efficient filter characteristics from free space into integrated optics on a small footprint and in a temperature-insensitive manner. Here's one example shown for polarization beam splitter that is quite effective with more than 40 dBs of polarization extinction ratio and low insertion loss of below 0.7 dBs from fiber to fiber. Here one example from quantum technologies where we have a filter that suppresses the pump light by more than 68 dBs in the waveguide on the integrated chip, which is very important for the generation of single photons and photon pairs. And a third building block on the chip that we use extensively is our micro-optical elements, where we have graded index lenses, so short pieces of graded index fiber that we polish to an exact length to act as a collimating or focusing lens that are inserted into the PIC itself in order to realize free space sections on the chip, where we can insert basically whatever we like. For example, isolators, as here, with lower than 1 dB on-chip loss in forward transmission and more than 40 dB peak isolation. Another thing that we can integrate using this approach are periodic cold crystals for nonlinear optics. And yeah, with this, I already come to some examples that I want to show to you today. One example here from communications as a photonic engine for transceivers. This is part of the terrific EU project, where we have waveguide ratings as the multiplex and demultiplex functional building blocks on the chip. And these are used to couple arrays of externally modulated lasers and waveguide photodiodes in order to realize transceivers for next generation data centers. And here, one example with 8-channel photodetectors and 8-channel EML arrays demonstrating 800 gigabit per second capability. And in the next step, we realized a 16-channel transceiver, again, using the same building blocks that we developed for the smaller versions, using a bigger polyboard chip. And yeah, this is also one great advantage of the hybrid photonic integration technique, is that you can have the active elements where you need them. Here you see these small arrays of active elements and this big chip with just the passive waveguides, which gives you a great cost advantage compared to monolithic integration for these kinds of applications. And of course, you need to also assemble it. And this is something that we are also automatizing together with partners, in this case with Ficontech, where we have automatic contacting of the arrays, automatic fiber insertion here into the chip, active alignment of the EMLs that you see here. Same being done for the photodiode arrays that are also actively coupled to the chip, cured, and then you have the optical subassembly. So this is also one important thing that you need to always take into account in hybrid photonic integration. Here, another example from a European project, TerraRay, which is for microwave communications. So this is a hybrid photonic integrated chip that generates microwave radiation for example, 6G networks. Here again, we have these tunable lasers that are introduced. We have the optical isolator on the chip, a quite unique functionality. We have a modulator PIC from indium phosphide, an antenna PIC from indium phosphide, and then finally a triplex PIC from silicon nitride from Lyonics. And I mean, even though you see here various indium phosphide PICs, these are all optimized for their respective functionality. So these modulators are optimized for modulation. The antennas and photodiodes are optimized for their functionality, and the gain shifts are optimized to generate photons. So again, underscoring the advantage of hybrid photonic integration for these kind of very complex integrations. And one last example here from Quantum Technologies. Here we make use of the micro-optical bench, where we insert quite a large periodically cold KTP crystal that generates photon pairs from an input of 775 nanometers, generating photon pairs at 1550 nanometers with orthogonal polarization that are split by these polarizing beam splitter that I introduced earlier. And the pump light is suppressed by the thin film element with more than 60 dBs suppression on the chip. And indeed, we can demonstrate photon pair generations using this approach in a hybrid photonic integrated way. And these photon pairs are then available for more complex processing in the waveguide on photonic integrated circuits. And yeah, with this, I'm already at the end of my talk, and I'm looking forward to your questions.
Okay, Moritz, thank you very much for the nice introduction and for the great talk. I mean, it's always fantastic to see this truly polyvalent polyboard that you guys are working on at HHI. And indeed, now we have time for questions, as after each talk. Please use the button to raise hands at the bottom of your Zoom screen if you have a question in mind, and then I pass you the word. And in the meantime, I'll just ask Moritz quickly. So, what are the limitations of such platform that we should know about in terms of maybe size, thermal budget, and these kind of things? And what's the overall technology readiness level for commercial use?
So in terms of small scale PICs, I would say this is already in the field for some applications. I mean, the very complex PICs that I've shown you before, of course, these look impressive, but they are from research projects, right? One thing to take into account on a technical level is, of course, in this case for these passive waveguides, switching speeds are limited by the thermo-optical effect, so in the order of kilohertz maximum. So this is something that the applications then have to live with. I've shown examples where we also coupled then the indium phosphide modulators next to the polyboard chip again in order to achieve more high-speed modulation. And this can then go up to tens of gigahertz. So there are things to keep in mind, of course, but there are also ways to circumvent it, again, using the flexibility of the hybrid integration.
Okay, I see now. Thank you. I see there are a couple of questions in the chat. Maybe Amir Gajimi from Lithium. Would you like to ask one? Yeah, I can unmute. Yeah.
Can you hear me? Died from Lithium. So yes, more. It's great. It's nice to see you again. So what was the transparency window of these polymer platforms?
Yeah. So transparency is usually from around 450 nanometers. So blue up to around 1620.
But not mid-infrared, right?
No, mid-infrared not. No.
Okay. And these are different polymers for shorter wavelengths, or the same polymer is from blue to 1600?
This is the same polymer, yeah. I mean, of course, there are some spectral features in the spectrum if you scan it from the visible up to the infrared, but you can consider it transparent roughly in this range.
Okay. Cool. And the power handling?
So we have high power tests at 1550 nanometers, where we have used up to 23 dBm.
23.
Yeah. So this was okay, and we also use it for applications where we have femtosecond pulses, and we do not see any issues there. So very high maximum peak powers, and we do not see any issues.
Thank you.
Okay, you can raise your hands again if you have questions. I think there is one more in the chat from Roronis from Thessaloniki University. Can the butt coupling be used for mass production? He's asking.
Yes, I would say so. So that is why we are also closely working together with equipment manufacturers in order to have processes that are in the end scalable. So the process that we develop here can then be directly transferred to machines that are specifically fabricated for manufacturing. I mean, the machines that we have here at HHI, of course, for R&D, but the processes we use can be transferred.
Okay, maybe last question from the chat. From Mehrat Boshe from Aix-Provence University. Do you think you would need the nano-imprint lithography technology for future to replace your technique, and how?
Yeah, we have it and we are investigating it. Yeah, maybe in the next meeting in 1 year's time or so, I can show some results on that.
Okay, sounds good. Looking forward to that. Okay, so with this, we thank you, Moritz, again for the very nice introduction. Always good to have you with us. And I mean, the next technique is also very exciting and again serves as a very nice example of the efficient hybrid photonics. So this technology is developed by Exceliprint, and Ruggero Loi, the supply chain scientist from Exceliprint, will tell us more about it. Hello, Ruggero, whenever you're ready.
Thanks for the kind introduction, Ivan. I will start sharing my slides for today. You see them?
Yeah, just go full screen.
Yeah,
and
we'll go full screen now. Right, so here today I'll try to give you an overview about the last advancements in microtransfer printing and how we're working to bring the technology in production. So the core technology, as you might have heard, is microtransfer printing, which is a pick-and-place technique based on the viscoelastic properties of the PDMS, of a PDMS stamp. Our business model is licensing of the technology. So we sell the technology for you to create products with microtransfer printing inside. Aside of that, we provide a few services. Example, development of microtransfer printing solutions, which means how to make your components or substrates microtransfer printing compatible and how to develop the microtransfer printing process itself. We also provide microtransfer printing services. We have a few tools at our headquarters in Ireland, in Cork, Tyndall National Institute. So we have access to the clean room of the research institution. We also have a subsidiary in the Research Triangle Park at Micros in North Carolina, where we have another few tools and the development center for the tools, which is actually led by our sister company called X-Display, which is also focusing on the microtransfer printing for displays. Everything else belongs to us in terms of development. In terms of numbers about Exceliprint, we have 700 plus patents, 100 million plus in development, 18 years of commercial development, 85 customers funded project, 200 plus many years of experience, and 20 plus printers worldwide. This number is actually doubling in the last 6-12 months. As we had many requests, especially in Europe and by new RTOs and companies interested in developing new solutions on MTP. In terms of projects, we are directly involved in a number of EU projects, example Inspire, Ambrosia, Baman, the M-Engine. And we've been involved in a successfully closed project in the past. There is also a good number of projects that we support from the back, but we're not directly involved in them. And this is showing how the ecosystem of partners working on NTP is able to work on their own on the technology and to develop new solutions, which is also showing how the maturity of the technology is increasing. We're also collaborating with pilot lines, or there are numbers of EU pilot lines that are adopting MTP as a standard technology in their offer. In particular, we have recently the Photonics Fab, which is actually building a small supply chain for the indium phosphide integration on silicon nitride and potentially on SOI through microtransfer printing. There is also a number of projects with industry. It's usually about 20 between new projects that come in and projects that close. So how about the microtransfer printing process, how that works? Well, for integrated photonics, we can imagine that we choose the target layout, so the PIC layout, photonic integrated circuit layout. Starting from that geometry, we can build or fabricate a source wafer with the devices to be integrated that will have a pitch matching the target layout. After fabrication, the chips are usually released by eroding or etching usually a wet etch, a sacrificial layer. An anchor system holds them during the undercut, holds them to the substrate during the undercut. So the final result is a suspended coupon that can be picked up and transfer printed through a PDMS stamp, which also has it's usually patterned with a layout matching the source wafer and also the target wafer. In this way, we can mix and match different materials, different device thickness on the same platform. In particular, we can integrate many components in parallel, increasing throughput and making the technology particularly suitable for high volume heterogeneous integration. Usually the last step of the process is the electrical interconnection. The optical interconnection is achieved by passive alignment and through alignment marks and pattern recognition. So here I just wanted to give you a visual example of the technology. So here we have a source wafer where we pick up 2 coupons, part of a larger array, and through alignment marks position on the target and on the coupons, the pattern recognition elaborate the correct alignment, and then we go down with this transparent stamp made by PDMS, and we're able to release the coupons on the target. Pick up and release are basically dependent on the speed of the stamp. The speed that the stamp is peeled off the substrate. So basically at high speed, we're able to generate strong adhesion to the coupon and pick them up. And by peeling off slowly the stamp, we're able to release them in the target substrate. So why using microtransfer printing for integrated photonics? What the main features and benefits? In particular, for the starting wafer, we can accommodate, usually it's a 3-5, so pretty expensive material. We can accommodate a highly dense array of components, so we can increase the source wafer exploitation. We can also fabricate the devices completely before transfer, which allows non-good die. But it's also possible to integrate coupons of material and then post-process them on the target wafer. In terms of transfer, as I said, the technology allows parallel integration of many devices, and we can also mix and match different materials and stack, giving the technology high throughput and flexibility. In terms of printing, we work with passive alignment. We can reach below 0.5 micron. We're already working on a strategy to reach 0.1 micron alignment, so 100 nanometer. We already demonstrate that for a single post and small arrays, but still it's R&D level. This technology is not used in production yet. So in terms of microtransfer printing integration of photonic device over substrate, we did that again for operational devices or just material, single post or as arrays. The type of substrate where we integrated these 3-5 or other components are silicon, silicon dioxide, glass, gallium arsenide, indium phosphide. Also SOI, silicon nitride on insulator as well, thin film lithium niobate. Basically, for the integration, you can proceed in 2 main ways: by integrating the components directly on the platform, or enhancing the adhesion through a thin layer of adhesive, which is usually around 30 nanometer, but it can be as thin as 5 nanometer. The light coupling scheme that we can reach with this technology is edge coupling, evanescent coupling, and grating coupling. The interesting thing is that we have these small devices that can very thin because we only transfer the epi, and we can basically integrate them on chip with this light coupling scheme. So you can have an edge couple laser on chip. I will show you some example now. So here we have a laser indium phosphide integrated in a recess, boot coupled to a polymer waveguide, and then evanescent transfer the light to an SOI. Here you can see the laser lighten up and the light coming out of the SOI waveguide at the other end. We also show that we can integrate in electronic integrated circuits, photodiodes, pixels. We can create interconnects with LEDs, PDs, and polymer waveguides. We integrated PD cells. Some more recent nice results from the Lumos project. We had some edge-coupled different components like PDs or modulators, amplifiers, etc. Another nice example from the Caladan project, integrated circuits on the silicon photonic platform from IMEC, where it's also integrated with quantum dot lasers. That is also integrated with quantum dot lasers. And so these enable a so-called co-packaged optics layout for specific application. Also, we had a nice example of some of the partners in the ecosystem. We are trying to build a value chain for or build this supply chain for microtransfer printing, where partners are Tyndall and Cornerstone integrate these photodiodes coming from Tyndall into the Cornerstone platform with 3 different light coupling schemes, the 3 main one that I mentioned. Here we have one of the first laser integrated boot couple on chip with an SOI waveguide with less than 100 nanometer overlay. This last example here is the laser integrated by Rockley, very high TRL in this case. We are at about 8, 9. So the laser was close to go or ready to go in production. As you may know, Rockley had to shut down the research center for obvious reasons. So this project was stuck, but we're working to move forward on this activity as well. Some last result in the last 2-3 months, IMEC shown, or the Photonics Research Group actually shown a nice approach to integrate the same SOA 3.5 over different photonic platform, in particular silicon nitride and lithium niobate, by integrating the 3.5 over a silicon photonic interface. So with a double integration, heterogeneous integration of silicon photonic interface and 3.5, you can basically integrate the same 3.5 over a different platform and get the same functionality or similar functionality. Another nice example is the come from the collaboration between Tyndall and Intel. So they integrate an O-band EBR laser on silicon photonics. So they basically integrate a coupon of material and then post-process them after printing, similar to other work made by Intel. So the results is very promising and is moving forward. It's been published recently. Another nice example is the EAM, evanescent EAM shown by Tyndall more recently as well. So, and finally, to close, as I mentioned, we are working to create a supply chain by working with all our partners in the ecosystem that are focusing on microtransfer printing. So the main goal, again, is to accelerate microtransfer printing in production. Why? Because of our business model, which is licensing. We will get more revenue as more devices or products will include the microtransfer printing in production. So the supply chain was built, again, by leveraging on partners already working on NTP, but it's not excluding companies that are interested into adding MTP to their portfolio. So the main activities at the moment consist in monitoring, supporting the suppliers, and facilitate networking between them to satisfy customer needs. As you could see from this diagram at the bottom, we have 8 main areas. At the moment, we include about 50 active suppliers, but we classified about 150 in total. So the main areas are components, substrate, MTP printing sites. For example, XFAB is going to be the site to scale up the volume once we will have enough volume for integrated photonics. We are also working with thin film interconnects partner, design partners, packaging partners, testing, and equipment provider. So if you're interested in joining this in using microtransfer printing and be part of the value chain for it, feel free to get in touch, and we will see what's the best way to work together as we move forward. So finally, NTP is a key enabling technology for integrated photonics. It's demonstrating to be quite valid and promising for it. We have multiple licensees moving in commercialization at the moment. We should have the first product out in end of 2024, beginning of 25. So with that, I think I'm done for today for this presentation, and I'm happy to take questions. Can't hear you, Ivan.
Ivan, you're still muted.
I think you're muted.
Oh, yeah, sorry. Yeah, so thanks for the presentation, Ruggero. Great technology, nice presentation. I'm sure there'll be questions. Please just push the raise hand button at the bottom of your screen. There is one already from Jorn from Epiphany. Jorn, would you like to ask it yourself?
Yes, sure. So thanks again for your presentation. It really looks like you have a nice mix and match of technology that you could enable. Yeah. So yeah, we as Epiphany are a photonic design house. So the question would be, what restrictions do we have when we need to design for your technology?
Yeah, I mean, main restrictions, well, at the moment, we're working on standardization because, as you can imagine, this is an hot topic. But main restrictions are in the printing spot characteristics or parameters. So the area on the PIC, for example, where you like to integrate a laser or a photodiode, there might be some geometry restrictions, but nothing fancy. It's all standard processing. And main restrictions for devices is that it might seem obvious, but you have to think about the device as a coupon, which means you have a perimeter for all the parts of your device to be included. So that means that if the coupon, let's say, is long 1 millimeter and 80 micron wide, means you have to arrange contacts, waveguides, and facets, maybe all within that profile and within that geometry.
All right.
Hope this answered the question. Yeah.
And how do you supply, for example, the designers with these restrictions?
We have a set of documentation. We can work together with designers and fabricators. So that's the idea as well for the supply chain to bridge the gap, and put in contact all the partners that are working with microtransfer printing and accelerate the whole development. Yeah, I mean, in terms of what we provide to designers, there is no special rules, as these are photonics devices and photonic integrated circuits. So standard process apply. Again, we have a few restrictions, but we have guidelines and documentation that we can provide to design partners for developing standard building blocks or eventually PDKs or ADKs as well. Yeah.
Yeah. Thanks.
Okay, I hope that answers your questions. Anyone else? If not, I guess we think Ruggero.
Hello. Yeah, I have a question. Sorry. Can you hear me?
Yes.
Yes.
Yeah. Oh, okay. In fact, I wrote the question in the discussion, but it doesn't show. So I thank you for the talk. So I'm Jonghan from Huawei Technology France. I have a question. So about the microprinting transfer, is this really a universal technology for all kinds of chips with different materials and size? I mean, for dice of different sizes and materials, is do the parameters of the coupons grabbing, moving, and releasing, for example, the strengthen or the moving speed, etc. All kinds of parameters require a lot of adaptation tests to be stable. So this is my question. Or still need complicated parameters calibration every time, case by case. That's my question. Thank you.
Yeah, for integrated photonics, we have developed a microtransfer printing process for most of the materials and devices. So in that sense, we have an advantage. We don't start from scratch. So, we can leverage on the experience of our partners and of our company to support quick deployment of, for example, the Rockley laser was developed starting from the Tyndall laser. And, in a short period of time, we were able to have it in production. I would say the main adaptation usually goes between transferring the process developed in a research center into a production line, which has usually more constraints. But, we're working towards that as well, especially for the indium phosphide in the INSPIRE project. Smart Photonics is developing devices and, their process is going to be suited for a production line. So,
Okay.
Yeah.
Okay. Okay, understood. Thank you.
No problem.
All right. If there are no further questions, we thank Ruggero again for the great presentation. And
Thanks,
yes,
Ivan.
if you feel like you need the help of ExcelliPrint, feel free to contact him or me. Yes, so the next presentation will be given by Laura Horan, the staff engineer and product management lead at Vanguard Automation.
Thank you, Ivan.
Laura? Yes. Whenever
Okay,
you're
I hope
ready.
you can see my screen.
Yes, floor is yours.
Great. So I'm representing Vanguard Automation, and Vanguard Automation work on the photonic connectivity side of hybrid integration. And in this talk, I want to show you hybrid integration for photonic connectivity using photonic wire bonding and fast attached micro lenses. So photonic wire bonds are free-form optical waveguides which can connect two optical components together and perform the mode matching and compensate for any alignment mismatches. And fast attached lenses are lenses that are printed onto the surface or edge of your photonic components. And this is all done by 3D printing. So at Vanguard, we believe in passive alignment of components, using additive manufacturing with 3D printing to perform the photonic connectivity and assure low losses. So moving, yes. Okay, this slide shows our motivation at Vanguard, and we want to tackle today's packaging and assembly challenges. This diagram on the right-hand side pretty much symbolizes the challenges. So to find my pointer. So you see here the large mode field size of a single mode fiber, 10 microns. And then in the middle here, the smaller mode field size, of a silicon photonics waveguide, or elliptical mode field of indium phosphide waveguide. So you have lots of different materials, different mode fields, and to get low loss, you want to match your mode fields. You need, in some cases, to have low loss, high precision assembly alignment. You also need fast and useful packaging to make it manufacturable and to be reliable under various conditions, such as the Telcordia environmental testing. And because of this range of criteria, we see that over 70% of the cost of your product is really driven by photonic packaging integration. So Vanguard Automation supplies solutions for performing photonic integration via additive 3D printing. So we have two solutions, as mentioned earlier. On the left-hand side, the photonic wire bonds, which are the 3D freeform optical waveguides that can connect two components together, performing mode field matching and compensating for any offsets in your assemblies. We also have a very dense integration. The other solution is the fast attached micro lenses, which can be printed onto the edge or surface of your optical components and allow for a relaxation of alignment tolerances. So photonic wire bonds can compensate misalignments for up to ± 13 microns, whereas fast attached lenses can relax your alignment tolerances up to minus 15 microns. So I want to show in the next few slides the recent applications from our partners and ecosystems where they did hybrid integration using photonic wire bonds and lenses. This slide tackles the photonic wire bonds. You can see here on the top here, a recent paper from Rochester Institute of Technology, which was published at ECTC this year, where they did hybrid integration onto an AIM reference chip. So on this AIM reference chip, they placed two GFB lasers and connected these lasers to the chip via photonic wire bonds. And then again, coupled out from this chip to a fiber, also using photonic wire bonds. And this entire assembly had an insertion loss of less than around 4 dB. So you have 4 different interfaces, 2 connects with 4 dB loss. Benefit being you do not need to do active alignment for your active components with low loss. And also, because you use the same interface on either side from laser to chip or chip to fiber, you use the same PDK for your connectivity. Our ecosystem partner, Dream Photonics, have also been providing the same service for a number of years, where they do hybrid integration of lasers on chips and chip to fiber. I think recently they announced they have an ADK with Tara Semiconductor, where they're providing the service with Tara Semiconductor chips. Another example is our recent collaboration with Poet Technologies and Vanguard Automation. So in this collaboration, we are printing 3D micro lenses onto the Poet interposer to maximize the coupling efficiency between the interposer and the lasers placed onto the Poet interposers. These technologies couple and complement each other very nicely, because here Poet really focuses on having passive wafer level scaling and processes for their products. So here the lasers are placed passively onto the interposers, and the lenses work to maximize the coupling efficiency, meaning reduce power consumption, and also using less materials to create the interposer, so really reducing material costs. And finally, an example of Sumitomo Electric. So last year, Sumitomo showed at OFC the very first demonstration where a commercial optical module benefited or had a 3D printed component inside their indium phosphide devices. And so with this paper, they printed the 3 lenses inside the component and really tested these to show that they are industry proven and passed the Telcordia 468 standards, which means going through environmental testing, reflow soldering, die bonding, shock testing, and high power operation. And where Sumitomo saw the benefit here is to improve coupling efficiency, where they're able to reduce their losses by 1.5 dB per lens, pretty significant. Also relax their alignment tolerances up to 1.6 microns, and really reduce their chip size. They didn't need the spot size converters anymore on chip. They could use the 3D printed lenses for this and make their chips 25% smaller. So we've shown compatibility with a wide range of materials and platforms with different foundries. It's not all of them, it's a simple selection. So each of these examples, there are 3 here, you'll see fiber on the left-hand side and chip on the right for AMF. Similar for Ligantech, chips on the left here, fiber on the left and chip on the right. And in this example here with Mentech China, you have fibers here and a wave diode on the right-hand side. And for each of these connects, we have 1.5 dB loss for fiber to chip. Actually, the Ligantech results are new from today. You can see here the range of losses for transmission for these loopbacks on chip. On average, 1.5 dB loss. So we have a path to implement photonic integration with 3D lithography for customers and partners. And we do this slowly to really implement the technology into industry. So the first step, we recommend that the industry keeps their standard production process steps and simply adds 3D printed elements with active alignment into their photonic products. And the idea here is to prove coupling and yields, but also to prove the components for all different testing and requirements that the customer might have. In the second step, we remove the active alignment necessary and do 3D printing with passive alignment with relaxed alignment tolerances up to ±15 microns, so showing the customer that passive assembly is a viable process. And in the third step, we move to photonic wire bonding and really get the full benefit of relaxed phase tolerances of ±30 microns with a very compact coupling, very high yields, and a high packaging density. This is all done with the Vanguard Symphony, which comprises of an array of machines for the 3D printing and pre and post processing of your chips, full software for machine control, process development and management of your processes, a full suite of materials to do the 3D printing and encapsulation, and all professional services, training, feasibility, collaboration, process development, and support and maintenance. And finally, I just want to say that next week we meet us at ECOC in Frankfurt at booth C104. And also we have the market progress talk where you'll hear much more detail about next generation photonic integration from Sebastian Skyfeld. And lastly, questions, but also in terms of what we can do for EPIC members, what EPIC members can do for us. We're looking for collaboration and opportunities where we can really show that this technology is industry viable and works for a wide different range of customers to bring this technology from where it stands into a viable industry proven production process. So thank you.
Thank you, Laura. Great presentation. Very exciting technology you're showing us. Let's see if there are any questions in the room. Please push the raise hand button. In the meantime, yeah, I'm wondering, maybe you can say a few words about the throughput of the machines. How fast can you do this wire bonding, in fact?
Like wire bonding. I think actually you saw the demo at ISDM in June this year. So we demonstrated there a chip-to-chip with about, I think it was 10 seconds for detecting the two waveguides, and then around 20 seconds to print the photonic wire bonds. So depending on your mode field matching, depending on the space between your chips, depending on a wide variety of parameters, can be from 20 seconds up to around 3 minutes. So depending on what you want to connect together.
Per chip. Okay.
Per chip, yeah.
Well, that's impressive. All right. I see there's a question from Stefan Lugen from Meta. Please, Stefan.
Yeah, my question is about the alignment. The passive alignment is pretty coarse with 15 micrometer. What can you get with active alignment? Are we talking significantly less than micrometer, 50, 100 nanometer, or what is the CPK that you can get here?
I need to step back a little bit. So what we're doing is we allow customers to have passive alignment by doing the connectivity with 3D additive manufacturing. So we can detect your waveguides, where your waveguides are placed down to 100 nanometers. But where we detect them, we can print from that point. So print together photonic interconnect between your two chips. So it doesn't matter for us how you align. You can have up to ±30 microns of misalignment and still have the same insertion losses or connectivity between the two components.
But when one is the height, where you say, okay, you can pre-select with a certain classes and say they match with maybe 100 nanometer in height. But how about when you have a lens, you need X and Y and Z for the active alignment of the optical lens when you put it in front of an DBR laser or something like that?
So then depending on the design of the lens, so depending on the size of the lens, you can compensate misalignments from ±1 micron up to ±15 microns. It depends on the mode field you have and the size of the lens you like to print, how much you like to expand your beam. This answers the question.
Yeah, okay.
Okay, good to hear. Maybe now a question from Andrew, Lightwave Logic.
Yes, hi. So just briefly, what is the general range of temperatures for the process of the wire bonds for the chips in manufacturing?
The range of temperature it can survive, you mean?
Range of temperatures for the actual process of printing the wire bonds. So, yeah.
So we generally do this at room temperature.
Okay.
So we stipulate that the customer has a room temperature of around 21 degrees plus minus 1 degree Celsius. That's the specification. But no customers print also at colder temperatures and also at higher temperatures.
Okay, very good. Thank you.
And yeah, Stefan, do you have another question? No, not yet. I'm wondering, maybe last question, Laura. Yeah, so yeah, first of all, yeah, this temperature that we just discussed. So locally, there is also no temperature applied to the wire bond.
No. We do everything at room temperature. But you also the machine is enclosed. As you've seen our machines, they're enclosed in a metal encapsulation. The temperature inside remains relatively stable. You also monitor temperature in real time to ensure temperature.
Okay. And then do you provide at Vanguard this as a service? Like if somebody wants to just try and do a photonic wire bonding on their chip,
so we're very open to collaboration. We really want to show the technology is working, so we're open to collaboration. We also have a network of ecosystem partners that we can also provide you with the names and help and support you to bring your process to their systems if it's a larger amount, a larger volume.
Okay, and you would be the right person to contact for this queries.
Please contact me anytime.
Okay, very good. Thank you for the answers and the great talk. And I now pass the word to the next speaker, which is Jörg Smolensky, the Business Development Manager from Nanoscribe. Jörg, if you're ready.
Hello. Yes. Hello, everybody. Let me quickly see that I choose the right virtual image. I think this is one. Yeah. Can you see my image?
Yes. Good.
Okay.
All yours.
Good. Yeah, I'm Jörg Smolensky from Nanoscribe, Business Development Manager, and I'm going to talk about fabrication of optical interconnectors for PICs to enable low-loss coupling solution, and this in a very easy way and possible. But first, let me start a little bit about Nanoscribe themselves. We are 15 years old. We introduced the printing technology in 2007 to the market. We have more than 250 systems installed worldwide, 100 employees, and we have a subsidiary in the US and in China for service and sales. Yes, more than 4,200 square meter space for office tests and feasibility studies in order to prove what we are doing. A little bit overview. Beyond this, what we are doing here is we have these kind of printing technologies used for life science, microfluidics, microneedles, material engineering. So we see some MEMS devices here, a lot in micro optics, and what we talk about today is photonic packaging and photonic integrated circuits. And I will explain this a little bit more where we are placed there. So integrated photonics, as I have already explained a couple of previous speaker, Moritz from HHI, for example, is a product which is based on different components, and you need to mix and match the different mode fields and diameters. So in the end, you will have a package prototype like we have here from the handheld OCT project, where you have the die. Let me quickly put on the laser pointer, where you have the PIC here on top, a fiber connector, and then we have basically printed here, as you can see on that side, some optical lenses in only in order to do free space coupling in this case. So it's not fiber coupling, it's order free space as it is for an OCT systems. So we printed precisely aligned this kind of optical elements to the waveguide, and Mark, I don't remember exactly, ask what's precision. So this is with a detection precision of 100 to 200 nanometer, precisely aligned to the waveguide. So this basically means we can print on any material, silicon nitride, silicon on isolator, any component, the PIC itself, a laser, a VCSEL, a photodiode, a single mode, multi-mode, polymer, polarization maintaining fiber, It can be 2 seconds, but that depends on the optical design of the lens we print or the connection. For this, we have developed the micro 3D printer Quantum Align, which is basically a printing product, where we have also resins and other accessories in-house developed by us. And this is always a supporting patent for portfolio. So coming now to what this means for you. So we can provide efficient light coupling solutions on fiber arrays. So on the left side, you see a fiber array with 8 channels. I'll explain a little bit later. We'll see later on. This can be on the chip edge, as I've shown previously, or it can also be on chip surface. So grating couplers or even replacing grating couplers. So fiber arrays, what do we do there? We adapt the mode field diameter and the numerical aperture of the fiber array, which is 3 micron to 10 micron size, and we have to adapt, as Laura showed it, to the small diameters on the waveguide, for example. In this, we have a very easy software, Nanoprint X, where we define the lenses via a formula. So you can see on the upper area, or you can just have the object you want to print, the object, it's micro lens or anything else, and load it into the software. We mark the alignment feature you need. In this case, for fiber, this we align to the core with less than 500 nanometer precision. You select process parameters. There's a ready-made set for every requirement in the system, the software already available. Then you just print and you develop. So we use a honey-like resin. You just drop it on the fiber, and then we can print. I'll not show this. You're welcome to contact me, and we can set up a demo, and I can show you online or on site in Karlsruhe if you want to. So in the middle, you can see some results. Fiber array, you see some SEM image of collimating lenses. Print time here is roughly 25 to 45 seconds. And you can see some periscope lenses, very low loss, less than 1 dB, where you can, I think it's a little bit more due to your optical areas, 80 to 90 seconds roughly. Here on the right side, you can see also that we do some characterization. So we have basically 2 characterizations. We characterize the optical element, that means the roughness and the shape accuracy, but we also have an in-house setup where you can see this in blue a little bit on the line here on top, where we can characterize the beam propagation of the fiber and also for a chip, for example. And then we do a design with an in-house code to have the lens adapted for the requirements you need. And then we again measure it, what we printed, and you can see that the measurement and simulation fits quite well. This is a case for 1550 nanometer. As usual, we also have a proof for environmental conditions, thermal shock, or humidity testing. That's all standard. Some images now to show the flexibility. So here you can see on fiber printing, periscopes. This can be multiple lenses, lens set here, or the taper for the butt coupling, things like that. Periscope array. And this is a design by Print Optics. We don't only print on normal fiber arrays, but we can also print on endoscopes or multi-core fiber bundles, anything you can imagine. And this is a multiple imaging lens. So it's a little bit different than beam shaping. This is really imaging, giving an image back. So the quality of the resin is highly important. And you can see also that we can nicely shape even the surfaces on the side to have some kind of structured surface to avoid stray light with our proprietary processes. An image of coupling of lenses. You can see how nicely they are aligned. That was an in-house result print test. On the edge of a chip, what we do basically is shaping the beam from elliptical to round to couple to a fiber, or maybe to another PIC. So it's again in the software, you define the lenses, again with the formula or STL. In this case, you align relative to marker, so down to 100 nanometer precision is possible, depending on the design and on the printing speed also. And then also you need to align to the edge, and you need to make sure that you can print also precisely at the edge to avoid some shadowing effects. And then standard process parameters, print and develop. In the middle, you can see some results. These lenses I have shown already previously. And then here's some multiple lenses, a few minutes of print time for these lenses. Print print time here is a little bit higher, so it's 90, 280 seconds. Can be more. It really depends on your optical interface, and there we need to discuss. If you want to have on the chip basically a 1 micron, 2 micron, 3 micron mode field diameter, and we then do the print the lines adapted to this with our system, or rather it's our partners doing this then for you. This is again from handheld OCT, an image of the chip. This is a setup where we have printed lenses on both sides on a EPIC chip app. You can see a little bit here on the red lights, the lenses on the chip. And then you have a fiber array in front, and we achieve very low coupling losses here. Also, what we want to stress, it's not only on the edge and on fiber, it's on surfaces of chips also where we can couple or print elements. So the classical thing is the one here in the middle, basically a grating array, where we printed 308 lenses for a partner. That was a project together with Fix. And another thing is also what you can see in the software setup and the SEM here is kind of broadband coupler, which is together with Pixel Photonics, a customer partner of ours, where we can print a large array of these kind of couplers on wafers directly. Again, classical thermal environment conditions are available. Print time 60 to 280 seconds, pretty fast and easy to be set up. Again, here's some more detailed images of it. This was even packaged. This was for prototyping for a customer. Very fast setup to test different designs. We went from 100 lenses to 300 lenses in less than a year with different design shapes. Summarizing, so basically what we provide with our system or our system can do, we are system manufacturer. The system can do any kind of 3D printed free space micro octets with our proprietary printing technology, 2GL. It can be scalable manufacturing of lens fiber arrays. You have heard print time, so an 8-time fiber array can print several 10,000 pieces of it per year with a single system. And even this is not the end of the possibilities we have. There can be wafer level printing aligned to wafers, to markers. Fast prototyping, really, I think that's a very important thing to start new technology, new developments in PIC. Another thing which was mentioned before a little bit in the discussion, we also do masters with this technology for nil. So you can imagine something combined of prototyping and nano imprint for mass production. We have done different substrates. This is a silicon on isolator example from VTT. Other optics, as I mentioned, imaging optics on wafer level or directly on endoscopes or in different ways are possible. And the classical one where we started 5 years ago, our microlens array for 3D sensors, for example. So that goes then again into the mass production. So final thing is the question, what can we do for you? What can you do for us? I think that's a classical one at any EPIC meeting. So yeah, as I said, challenge us with your optical interconnect and packaging problem. Contact me or via our website, contact us. But I think the best next possibility is at ECOC. So we are at booth F43. And we will have a hands-on training session the day after ECOC on 26. There are still a few places available. So you're kindly invited. There's a link in here, and I can provide you also with the link afterwards where you can register if you're still interested. But it's really limited places available. So there you will experience the printing, the setting up of the process, the easy use, and the software. That's my proposal for you. Thank you for your attention.
Thank you, Jörg. Very nice presentation and exciting technology as always. Impresses me each time I hear about it. Are there any questions in the chat? Maybe for Jörg? Take advantage of the opportunity now. I see now there's one in the chat from Stefan at Meta. Stefan, would you like to ask it yourself?
No, that was from previous talk, one of the previous talks, so it's an old question. So. Okay, so here everything is clear for you now? Yeah. Okay, good. And then another one from Mefrant from Aix-en-Provence.
No, sorry. Yeah, actually, this was an old question as well. Okay, well, maybe just Jörg then explain us. Yeah, so I mean, you're very experienced in telling us, yeah, what we can do for you, and also what you can do for us. So you can provide also this as a service, right? So people can come to you with chips, and you can
Yes, most of the
demonstrate.
basic. Yes, we can demonstrate the capabilities. We have partners. There's Fix in Holland, Netherlands, who has a system, so they can do the printing on fibers, on optics. They have a web shop for fibers, for example. So you can order standard fibers arrays there with standard design for collimating or focusing lenses or anything you can imagine. You have seen the examples. And we have also Print Optics, which is another partner, which is they're based in Stuttgart. And if you're interested in being a partner or job shop with our system, contact me. If you have a challenge for optical interconnects, feel free to contact me. We can help you to solve it. Don't come too late. It's good to come in the design phase, I think.
Okay, fair enough. And maybe a few words on the future. What's the future of this technology, and where are you heading? And maybe there'll be a potential co-development project for your machines.
Co-development, I'm not sure. We have all the know-how on resin, software, hardware in-house. We work with a lot of different partners, engineering companies out there in the market. I think the future is really to bring this to mass production. This year, next year, in 3 years, depends on different projects. It's a unique possibility to reduce losses in PIC and to standardize a few connections also. I mean, as Sebastian Skassel said at the Optica meeting, recently, the biggest issue is really standardization in PIC, that you have the interfaces as a standard. And even for hybrid integration, for microtransfer printing, standardization of the optical interconnect will bring it forward. And I think this is something we should look at.
Yeah, here I agree with you. Okay, well, thank you very much, Jörg. Nice presentation as always. And with this, I pass the word to the next speaker, who represents Chilas BV. Dimitri Geskus, the Chief Technology Officer, will tell us about the ultra-narrow line width tunable lasers.
Thank you. Thank you for a nice introduction. Let me share my screen. Good.
No, we don't see it yet.
I have to find the OK button. There it is.
Okay, good to go.
Let's go. Good. Thank you. Thank you for a nice introduction. I'm Dimitri Geskus from Chilas. And at Chilas, we use all the stuff we have seen so far, the chips, the gain sections, etc., to make a tunable laser source. And what we do actually, we combine the high gain of a semiconductor optical amplifier. The most mature products of us use indium phosphide, and we have a silicon nitride feedback circuit, which schematically looks like this, and it has very low losses. So we keep the high power in the system and also out of the system for your application. And there are a few elements that tune the wavelength being feedback into the cavity. There are two ring resonators there, the slightly different diameter. So therefore, the filter response looks like a Vernier. You see it over here in the animation bottom here, that the rings slide over each other, feeding back only one of the wavelengths within the gain bandwidth of the gain section. And that laser light starts to oscillate back and forth, and you get a clean up of the spectrum, and you get a very nice single mode output with very low line width. So several products there. Right, it's not doing what I'm doing. There it goes. So within the 1500 C-band, in that range, we've got a fixed wavelength laser, tunable to any wavelength in the C-band with accuracy of 10 picometer. And gives us good output power and low line width. We've got a new product, which I will show a little bit more over here and also in the future. And that's the swept source, where we stitch all the wavelengths together into a swept source. And we've got a 100 nanometer tunable laser, which can be set to any wavelength within the specified range, exploiting really the wings of the gain spectrum, as you see over there. It's nice and compact, fits into a nice butterfly, an ordinary 14-pence butterfly. And for the swept source application, we have developed a piece of electronics and firmware to put it into a single module. There, the thing is soldered hardly in there, and yeah, so that's it. But what you can do? What can you do with a tunable laser? Well, you can do many things with a tunable laser. Can this ribbon be removed? I think not. Ah, there it goes. Excellent. One of the things you can do with this laser, you can make it very stable, lock on one wavelength, or you can do some FMCW for LiDAR applications. You have a small jiggle on the frequency, or you can motor-free tune the laser for spectroscopy and other applications, or you sweep all over the gain bandwidth available for OCT and fiber bragg-rating centers. So here you see a little bit of the graph. So fixed wavelength, very stable, wiggle around, FMCW, up to 1 gigahertz, 2 gigahertz of modulation depth, swept source for very wide range applications. Well, here we present the outcome of the laser when it's free running. Free running is it has stability of around 1 megahertz. So if you set it to a wavelength, it will stay at that wavelength with a jitter of, well, a wiggle around is typically thermally induced of 1.2 megahertz. And if you lock it, then you get up to the kilohertz regime. And you see nicely that for the low frequencies, the phase noise is reduced significantly. And you can also see that when you lock it to acetylene cell, it stays there for a long, long time. Well, this is very interesting for quantum application, quantum clocks, and other applications where you need ultra stable light for long-term stability. And there are several cavities in this laser. There are 2 ring resonators there, and there's also a cavity for the overall length of the cavity. And you can tune to any wavelength within the gain bandwidth. And here we have got a demonstration of one free spectral range of the cavity, which is stitched together, and we very smoothly tune all the heater elements. It's heater-based tuned all together to have a very smooth moving of the emitted wavelengths. Now, this is excellent for gas absorption or any very fine spectroscopic application. We embraced this method, and we stitched all the modes of the cavity together. And I think we'll go to the next phase of hybrid integrated lasers, is that you make a swept source. Here on the left bottom curve, you see the wavelength on the horizontal scale, and in the vertical scale, you see the output power. Now it seems a little bit jittery because this has been stitched some few hundred of free spectral ranges of sweeping all together, but there's some control on there, and then you see there's a little bit of jitter on the output power, but it scans this full 40 nanometers within 1 second. So actually every second you sweep through all these wavelengths with very, very high resolution. So the wavelength grid is only 4 picometers. So you go from 4 picometer steps all the way over 40 nanometers. And it's very accurate and very reproducible. This is from sweep to sweep. This pattern is there always. So to demonstrate that we really hit all the wavelengths, because we get a lot of questions about, do you hit all the wavelengths? Yes, we do. So we made this very simple setup. We took a fiber splitter and put the one branch into the HCN reference cell, and it has some absorption peaks there. We put it onto a photodiode set, and then we print it on an oscilloscope. And there you see that you retrieve in 1 second all the gas absorption lines. Now, this might not seem very impressive, but the impressive part is that these lines are very, very narrow. And it is really hard for a laser to really scan all of these lines and to resolve all the absorption lines there. And when we zoom in onto one single line, you see over here, the purple line is one of the measurements. So remember, this passes by for the full C-band in 1 second. And then you see these 4 picometer step sizes here. And the laser resolves the full absorption line of the predicted model. In between the cells, in between the points, the shape is a little bit deformed, and that is because from point to point, the wavelength sweep is not fully linear, and because the thermal-based thing, so a little bit of a shape there, but we can improve that by putting more points in between and let the lasers, scan more smooth over that thing. But at least this is. The laser line itself is around 5 kilohertz line width, so you can imagine how fine the resolution is we can scan over there. Now, for 40 nanometers per second, that's a little bit of a fixed speed we have at the moment developed, and we can also scan over subsections of the wavelength scan, and not doing the full 40 nanometers, but doing, for example, 1.7 nanometers. And then you get a rep rate of 24 hertz, which is video rate. And we've got the next setup for that. We take one of our micro ring resonators and we put the heaters to work and move the drop response of the micro ring resonator while we scan over the resonance there. So you see here on the blue side, on the back side, the continuous power on of the laser on the oscilloscope, and the red curve is the position of this drop response, this device in the test. And it gives a nice video there. And I'll take the guts to start this video. Let's see if it starts. No. That's a pity. Do I have to be patient? No, I'm not patient myself. I'll show it afterwards. And next to the video, we also have a lot of other wavelengths. Well, you basically take a silicon nitride chip and you glue any other gain section to it. And there, with that setup, we have several colors in the visible being developed. 680, 690, 707, and 780 nanometers for mainly quantum application there. Output powers are around 1 milliwatts, and the tuning range is around 10 nanometers. And this all depending on the gain sections available there. Then we've got the 850 line, which we have some lasers available. They tune about 25 nanometers. And then we have also a set which is tuning around 1700 nanometers with plus minus 50 nanometers tuning range. Now, briefly, we'll exit the presenter mode. Let's see if it works. Let's see if the video works like this. Now, I don't know if this. I hope I'm still sharing my screen there. But I think this is one of the breakthroughs we are having there, is that we can really video rate monitor some features of ring resonators there. And we can customize the laser scan motors for all the customers we have on our hands. And we're expanding our wavelength range and applying the lessons learned on this laser for the future as well. That was the end of my presentation. I hope there are some questions. We will have a demo at 8 o'clock in a week from now. And then we'll show you the swept source, obviously. And I'll aim to have some break rating sensors there, so you can touch the light and see if you are warm-blooded or cold-blooded. Open for questions. Thank you.
Yeah, thank you, Dimitri. That was impressive. Good that the video also worked. Yeah, a great presentation. And I hope we'll hear some questions now in the audience. Please raise your hands now. I see there is one from Marco at AFE. Marco, would you like to ask it yourself?
Yes, thank you. Very impressive product. I was wondering about the tuning speed. You mentioned at some point 40 nanometer a second.
Exactly.
Is there anything? Is it like thermally tuned? Can it go faster?
Yeah, it's a thermally tuned system, and we have obviously we are trying to get it even faster than this 40 nanometers. I think we can go a little bit faster, but not more than a factor of 2. These heaters have an intrinsic response time. Obviously, you can overdrive them a bit to speed them up a bit, but this is for now the speed we are offering. We are always working on fast actuators there. So we have some projects starting up on the background on piezoelectric and on lithium niobate systems, where the tuning speed is obviously much faster than in thermoelectric effects.
Thank you. Very impressive.
About the tuning speed, what is also nice is the laser has no mechanics. So basically you can hop to any wavelength you want to go within a millisecond. So if you, at the end of the scan, it hops back within a fraction of a millisecond to the beginning of the scan. So, and that also sometimes helps for, following features, that you take a subsection and you follow a part of your feature which you want to follow. That's, that's the way to come around with the tuning speed.
Yeah, perfect. Thank you so much.
Thank you.
Okay, sounds good. I have a question too. I mean, you mentioned several applications for these tunable lasers. So what's the main application these days, and what's maybe the upcoming one for the future? What do they find the use?
The main applications at this moment is we see a lot of traction going on for fiber graduating sensors. Any sensors, we've got some micro ring resonator sensors there in the field. And we also have a lot of traction on the very narrow linewidth, which is for some cases below 1 kilohertz. And there you get for quantum key distribution, get some traction there. And yeah, so there are a wild range of applications. Last time I got called and they want to generate terahertz generation. Terahertz, whoa! You everywhere where you need a laser, a tunable laser or a fixed laser, this type of lasers, they are of interest, I think. And again, we can pigtail them to your application very easily. There's a graphical user interface. We've got also an API, so all command instructions there to get the laser to your application. And if you want to go for volume, well, this is now assembled with using machine assembly. It's fully automatically assembled. But obviously in the future it will be flip chip assembled and even, transfer printed, that we get our lasers into any system, replacing all the lasers in the world. So let's aim for that.
Let's aim for that indeed. Okay, thank you very much for your presentation, Dimitri.
Thanks a lot.
Yeah, and please feel free to contact him if you would like to try one of those tunable lasers. And I pass the word to the next speaker, Andrei Paletinsky, the Principal Application Engineer from VPI Photonics, who will talk about the PDK framework from VPI. Andrei, the floor is yours.
Yes,
whenever
hello.
You're ready.
Yes, so welcome to my presentation. Thank you for introduction, Ivan. And yes, so today we heard quite a lot about the technology already, about the platforms dedicated for it and the product. But by now we didn't hear anything about the main part, which is connecting all of them, so about the design. And within my presentation, I will teach here a bit more on the perspective of how we can go through the platform to the design, and mainly how to account for this integration part, interfacing part between different platforms within the single design, within the single final chip we want to get. So very briefly about the company. So VPI Photonics is a software company providing the software solution for simulation, optimization, and design of optical circuits. And not only, but to this I will come in a second. We are also offering some services, some design services. So we are on the market over 25 years already with regional offices in Europe and North America, with a lot of the global networking resellers all over the world. We are mainly facing with the 3 I's. So firstly, integrate. So we try to really integrate all the simulation techniques, starting from the devices to the systems, enabling you the design not only from the perspective of the cross section through the photonic circuit, but also from the system perspective. So mainly how your PIC should behave in the whole system, where you will connect it with multiple other components like fibers or DSP afterwards. The second I is the interoperable. So we are trying mainly to make the interface with many different third-party simulation tools to not limit only you to the functionality of the program itself, but also to allow you mainly to interface with all other tools, for example, for electronic simulation, for layouting, and much more, which I will also mention in some examples directly. And the third, industry leading. So we are cooperating with many industrial and research collaborations to develop state-of-the-art PICs, also to set some standardization. And I will just show you few examples which are touching directly the problem of the hybrid integration here. So from our product perspective, I mentioned we are covering everything from the device to the system level. Today, I will focus only on the PDK interface, which are allowing us mainly to link the foundry dedicated components to enable the PIC design with them and fabrication of the chip afterwards. So very shortly about the PDK, in a standard approach, the foundry just provides some kind of the description of their processes in the form of some PDK library describing all necessary information, including the performance of the building blocks, layouts of them, but also the detailed description of the process that is created, that mainly reflects the technology steps in order to fabricate it. Based on this, there are some PDK compact model database created, and we are created simulation models for it. These models mainly take the information from either measurement of the fab or simulations. And of course, you want to bring this in hopefully some standardized format that will enable automatic creation of this generated simulation modules. Then once you are having the simulation models, you are of course building your circuit design, which you are interested in. And here I will come back to this example, but we see the reproduction of the widely tunable laser, which was shown by Moritz in HHI. But yeah, as I mentioned, I will come back to this. The idea is that mainly we can simulate the PIC itself, but we can also verify this PIC on the system level. We can co-simulate it with the electronics. And once we are happy with the design, we can extract the layout process with the layout design in order to prepare the GDS file, send it to the fab to get our assembled PIC. So now I will talk briefly about the different approaches which are used between different platforms in order to enable this hybrid PIC design. And first, I will start exactly with mentioning of this transceiver in that part, which is a bit extended version of the HHI laser shown before. But mainly, yes, we are interested in the final design, which you can see is already including some fiber component, including the coupled laser with the photodiodes on chip. But we start just with the building blocks. So how we do it, how we go through it. Yes, maybe one more thing to mention. You can see that within the PDK library for this polymer platform, we are already having some indium phosphide components. And that's exactly one of the typical approaches how foundries can enable directly integration of the platforms. So you are just building your polymer chip, which will include directly on top of it some additional gain sources, some additional photodiodes, or modules which are enabling direct coupling to the fibers. And based on those components, they are already optimized for the fab, and they can be fabricated and assembled by the fab directly. This means that after your simulation, after you can show the results which you are expecting, you can directly export the layout to one of the desired layout tools and process with the with the GDS generation. Please note that the GDS is including only the layers here which are belonging to the polymer chip, but you can see there are some predefined spaces which are enabling you directly the integration of these components with this different platform modules. And in that case, if you provide such design with additional information how this needs to be coupled, HHI the assembly everything and provide the final chip, which is assembled here within the polymer chip fabricated by them, and also the indium phosphide components created by their foundry of generating the structures indium phosphide. Okay, but what's happening to all other foundries which they don't really include the information about the standard component integration? So standard designs for the silicon nitride, lithium niobate, or polymers, they don't really have directly the modules which are being enabled there by the fab. And in that case, there are mainly two approaches by now, how you can make a design and fabrication. Firstly is directly talk to the fab and discuss with the fab what kind of building blocks they are offering. And here a good example was the design which I mentioned already before, although the building blocks were generated there in the PDK directly, but you can discuss about different kind of indium phosphide lasers or gain chips, which could be coupled there directly. On the other side, you can also use some external light sources. And here, there is another case, so you can find out many pluggable or bar chip lasers for visible light, a lot of QCL laser for mid-infrared, but there is one big issue with them. So there is no clear information how to build interface with them unless provided by the fab or provided by the laser manufacturer. So here we see some different laser sources which we generated between different projects with some structures for visible and short near infrared, for C-band, and also for the mid infrared. They all were optimized in that case based on the project work for given platform. If only you would like to use these components with some other platform, of course, this means that you need to build your own interface module. And let's show this how we can do it on the example. But first, how we could generate, in that case, a platform, a template of the PDK that could work for us directly by enabling generation of your own custom PDK. So here we have a process of generating such custom PDK. Mainly it will include some templates, it will include some additional layout information. And while you are creating your own PDK, you can easily protect the IP. You can extend the PDKs, the existing PDKs, and share them mainly with your own interest partners. And if you are interested in this process, please refer to the paper that we recently, the article that we published at the start of the year about mainly design freedom and IP protection using the PDK. And how this PDK can be used based on the example, I will show here the hybrid integration of the mode-lock laser using, on the left side here, we can see the silicon nitride extended cavity based on the Lionics. And here we have the SOA structure 3.5 based on the smart photonics. And this idea was mainly recently published, or recently 3 years ago published by the Vissers, mainly explaining on the design itself and fabrication of the structure. So very easily we are creating a library of the components. We are using, in that case, on the left side, the components for the silicon nitride equivalent with the PDK of Lionics. On the right side, we have the indium phosphide components equivalent to the smart photonics and adapted to the performance of the measured devices. And here we see one additional magic component, which is actually the spot signal converter between one and the other platform. I'm especially not looking into this component, but if you are interested exactly how it functions and what can be done here, you can refer back to the paper. It's described in details, including even some tolerances of the coupling and misalignment with the total map, how the coupling should behave. But for the perspective of the design, I would like to refer more that, of course, such combined platforms, we have some design with the combined with different platforms can be created on a single chip when you are directly simulating the performance. So here we can see our spectrum of our laser, we can measure the repetition rate and also observe the waveform very similarly to the ones which were achieved in the paper. And of course, what we can do on top of it, we can perform some tolerance analysis, either based on the implemented by the foundry tolerance analysis or by just varying of the interest and providing given tolerance analysis of our choice. In that case, I was using mainly the provided information from smart photonics on the tolerances plus some additional Gaussian variations on given components to investigate mainly how the frequency shift of the main peak, so the peak power of the whole spectrum, and also the maximum power of the spectrum will behave based on given number of runs. So to conclude with the standard approach, which was very often shown, what you can do for us. Firstly, of course, you can use our tool to develop your own PDKs and share them with your customers in order to allow them to really follow up with your designs. But also we will be very happy to get feedback from you regarding your design needs and regarding your PDK development, especially if something you believe should be added on top of the tool. And where we can help you, mainly we are helping here with enabling the various strategies for the peak design, offering the workflow from devices to the systems via, of course, circuits, and by offering you the custom PDK framework, enabling you mainly to develop your own components and interfaces to build the design and be able mainly to fabricate those integrated platforms directly. Just maybe short comment only on at the end, we are helping to accelerate this design together with the export to the layout, which we presented already several times before. And also we are offering the personalized support with the help to develop this PDKs. So if only you have some interest in those topics or many others, which I just listed, feel free to contact us either directly or via Ivan, or at ECOC, we are also there. So if you have any questions, please feel free to contact us, and I'm also happy to answer now if we still have time.
Thank you, Andre. A very nice presentation, very detailed. So yeah, I'm sure many people will try the VPI products after this. And yeah, let's see if there are questions. I see one from Dimitri. Please go ahead.
Hi, Andrzej, a very nice presentation. Always impressive what you managed to simulate. And I see you already have quite an effort on the Lyonics technology and 100 Hertz gain section material. I think we should sit together because I think it's easy for you to model some ring resonators there, right?
Yes, we also have example with Lyonics, with the ring resonators, with the laser fabricated by, I don't remember now, sorry, but with the free ring laser structure for narrow line with tunable lasers.
Yeah, I remember there was a project with Yao and Fan at that time, I think. Excellent. Very nice work. Thanks a lot for showing it.
Yeah, so I'm happy to talk to you either anytime now or at ECOC in person, so we can go in details there.
Let's do that. Thanks.
Okay, that's the spirit of the EPIC meeting. Okay, good. Thanks for your involvement and question, Dimitri. Anyone else? Okay, if not, indeed, I mean, you have an opportunity to meet most of us here at ECOC, I can imagine. So consider the information you got now, and we can talk in person. So see you there as well, Andrew, and thank you again. Now, before the last presentation, let me do a little intervention here with a couple of slides I'd like to share with you. First of all, I didn't mention that we have a sponsor of the meeting today, and this is the famous packaging house called Fix Photonics Assembly. They're located in Netherlands, and from which they supply the PICs and MEMS-based components and models in scalable production volumes. They can work with all kinds of PIC platforms, silicon and non-silicon based. They work from prototype to volume. They help to optimize the PIC designs and modules. And they also have world-leading expertise in hybrid PICs, fiber attachments, and ultra-high frequency electronic interfacing. So if any of these packaging services interest you, please feel free to contact Marcel van Veen, the sales director of Fix. And the second piece of news I have is that there is an upcoming PIC event from our friends Photon Delta, again in Netherlands. So on the 15th and 16th of October, they will have a great event, the 2 days event full of information on the photonic integrated circuits. So please come and join Photon Delta, EPIC, and everyone else in this exciting event. One of the most influential ones in Europe. And this year they gather over 700 visitors from more than 20 countries. So the program is again 2 days. It involves the speakers from famous companies as NVIDIA, Global Foundries, IBM, and Airbus. And on the second day, there are more dedicated sections, including a section on tech tour, next generation ICs, and a section on quantum integrated photonics and the future of integrated photonics. So EPIC is the strategic partner of this event. I'll be there myself as well. We'll be happy to see all of you in person. And EPIC members enjoy a significant discount for the entrance fee. So for this, you have to use the discount code on the right hand side called EPIC 15%. So hopefully see you in October at the PIC Summit. And with this, I'm done, and I would like to introduce the closing speaker of this session today. Jimena Garcia Romeo Nunez is the CEO of Alcyon Photonics, and she will talk about leveraging hybrid integration to accelerate photonics adoption. Jimena, hope you're with us. You just need to unmute and share your slides, and you're good to go.
Okay. Thank you very much for your introduction. Good afternoon. We are in Alcyon Photonics. We do integrated photonics design. And as most of you, I don't know, last week you heard this message from the VP of TSMC. They expect silicon photonics market to explode over the next years. And they understand that behind this, there is a strong pull from communications, but I also foresee a number of markets who's going to be behind this. And we all have heard of the power of integrated photonics. We all hear from investors, from analysts, that a lot of industries are about to adopt it. And for years, it's been a talk about silicon photonics. As we were discussing today, it's not silicon anymore. It's a number of platforms that we expect to be solving the issues of each application. And still, for some of these applications, it won't be one single platform. And very good example is everyone's talking about the next generation of transceiver, 800 gigabytes, and so on. And we all acknowledge that it's going to be a combination of maybe lithium niobate or some other platform for modulator, another platform for managing the signal, another platform for detectors. So it's true that one single platform is not meeting all the needs in market. So it seems that we all need having available designs so that customer can choose the better fit for the products. In that sense, that's what Alcyon Photonics does. We do master a different kind of designs techniques, which basically make us capable of designing very efficient designs. So we usually are very efficient at bandwidth and polarization management, and translating our designs from one platform for another. So being capable of bringing this IP from one platform into another. So we were born on a unique design approach, SWG, which means that we can manage light in a very flexible way, enabling a metamaterial approach to design. But we will also, we're born with a modular IP mindset, with the idea of that customer-led to be defining which functionalities are they needing, which performance they are needed. And for that, we decided to build a number of blocks and PICs, which include passive, tunable, and active designs through different materials, and now validate them through different foundries. So basically, we are a company which is making photonics design, those blocks or those PICs that PPA was mentioned before, that need to be combined to build an application along different platforms, because we understand it's customer choice to decide what's the better fit for each stage of its product. So basically, what we do is we do design. We do a very efficient design of different photonics elements. We are working with a number of commercial foundries on validating, making sure that they are very efficient, but especially making sure that they are reliable, because we do understand that in order to happen this massive adoption of photonics that everyone is promising for years, reliability is a must of the industry, so that customers can bring all this together into the final application. So in a nutshell, what Altium can do for you is, on the one hand, making sure that different functionalities are designed in an efficient way, bringing the best performance for each functionality, but also ensuring robustness through our agreements with different foundries, so that time to market when defining a new product, time to market for the next generation of application, it's gonna shorten for end customer. And in a nutshell, that's us. You can contact us if you're interested in bringing this new application into market, but also you're a foundry or a partner that requires from designs to make these capacities of yours easier into your customers, because making photonics easier for the future is what we do at Altium.
Okay, great. Jimena, very, very good presentation. Can you hear me?
Yeah.
Good. Okay, thank you for the presentation. Maybe any questions? Then I'll start with the most important one. Jimena, so what can you do for us, and what can we do for you as EPIC members?
As EPIC members, as we mentioned, and we are in conversation with some of the members, is how we make more easier photonics, how we make IP available for end customers. Not everyone needs to have a PhD in design, an MMI from scratch. That's basically what we do for others, in collaboration with foundries, so that and because learning is that customer choice where they're gonna scale. So that's what we can do for everyone here, and what we expect from you is, let us know if you find a roadmap somewhere we have not explored yet, and we mentioned some of the things we are doing, but we are open to explore new materials and happy to bring that into life.
Okay, that sounds like a nice motto. Okay, thank you very much, Jimena. Any further questions? Because if not, we're hitting the 2-hour barrier now. So I'd like to thank Jimena and all the speakers of this session one more time, and just quickly share a few things with you. So this was the online technology meeting on hybrid photonic integrated circuits presented by EPIC for you. So just to remind you again, EPIC is there to help you with technology, consultations, market studies, networking opportunities, mentorship, recruiting, and investment opportunities. So this was made possible by all the team of EPIC, my brilliant colleagues here. And just one more reminder for you, the 15th and 16th of October, we have a PIC Summit Europe coming. So please join, and please don't forget to use the EPIC 15% discount code. With this is the end of the event. Thank you very much for your attention. Thank you for staying with us until the very end, and hope to see you on the next occasion. Thank you.
Thanks a lot.
Bye. Thank you.
Yeah, at this point, yes, we stopped the recording, so the meeting is available, will be available later also on YouTube. So I hope all of you got some information from this. Again, if you miss any contacts, you want to get in touch with our speakers, or you have any other idea for collaboration, don't hesitate, let me know. Also, the room will be available for a few more minutes if you want to have a discussion with someone. Now you have the open mic session. Thanks. And yeah, like we discussed next week at ECOC, don't forget to register for the Epic reception at ECOC. Please join us for the product release session we have there, and for all the other Epic events organized. So looking forward to see you in Frankfurt. And I think out of the speakers, everyone is coming. Basically, that's what I understood. So we really gathered in time now. Yeah, good.
Ivan, goodbye. Thanks for organizing.
Thanks, Jörg. Goodbye. We see each other on the next occasion.
Yes, at ECOC.
Frankfurt.
Goodbye.
Yeah.
Laura, goodbye.
Ciao.